Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 32, and this is actually also the last lecture for this course. So, we are going to continue with the theories of failure. So, let us work out a tougher problem in this lecture. So, we have to design what is called the lever. Okay. So, a typical lever will have the following shape. So, it has got a shaft, and then this has got an arm here, all right. So, this is the handle which is used to grip through our hands, okay, and we apply force to this handle, all right. So, this can be used to turn, and the part over here, this could be attached to some machine, all right. So, the handles are usually quite rigid, and it is this shaft which is deformable. Okay. So, we have to design this shaft. So, suppose that this has to be used in applying some force F. So, in a machine there will be a maximum force, let us say 100 ton, 200 ton or 400 ton. So, we have to apply that particular force through this handle, and there could be a factor of safety also, let us say if n is equal to 2. So, if we have to apply 100 ton, then we have to design for 200 ton, okay, so that we never really reach the critical limit of 200 ton. All right. So, the factor of safety being n, so we have to design for force equal to n times F. Okay. Now, let us put coordinate system here. So, this is your I axis of the cylinder. Well, we can call it k also, because if you use cylindrical coordinate system, then that is your z axis, and then we have I and j in the cross section, all right. So, the force that we are applying here, this force vector F is then F j, correct. So, for designing the shaft of this handle, we have to think of what are the forces and moments that acts in the cross section of this shaft. So, let us cut a section here, okay, and look at the remaining part. So, here is the section of this shaft, and we are applying this force F here, and then at this end we will have negative of shear force V, correct, and negative of bending moment M, because that is the negative cross section, is not it. So, when we do net force balance, so net force balance that implies minus of shear force V plus F j is equal to 0, which implies that the shear force is equal to the force applied F into j. So, shear force is acting in the j direction. Okay. Now, what about the moment? So, when we do moment balance, let us say about the center of the cross section over here. So, about this point. So, we will have minus of m, correct, plus the moment due to the force F. So, how much is that going to be? So, suppose that this length over here, that is h. Okay. So, we have plus the arm of the force F. So, that is L minus x k minus h I. So, that is the arm of the force. Cross product, the force itself F j. So, that is the moment due to the force F, R cross F, and this has to be equal to 0. So, this implies the bending moment m is then equal to L minus x k minus h I cross product F j, and finally, this is then equal to minus of L minus x into F I minus h F k. Okay, so, bending moment has got two components, one along I and other along k. So, that is a total moment. So, this part is actually the bending moment responsible for bending the beam, and that is m x, right, it is in the I direction, and this part, that is the torque, because it is along the axis of the beam, torque T, and then we have shear force also, you can see here. So, that means this is V y. So, V y is equal to force F. Okay. So, we have not only shear force in the cross section, we also have bending moment and the torque T. So, what are the various stress components that generates due to these loads in the cross section? So, due to shear force V y, we will have shear stress tau z y, right, on the z plane, on the cross sectional plane and in the y direction. Let us draw the cross section. So, here is your cross section, and then we have I axis and j axis in the cross section, okay. And then the shear force acts in the j direction. So, it is going to induce shear stress in the j direction, correct, and that is tau y z, right, on the z plane in the y direction. So, we have tau y z. Okay. Now, due to bending moment, what are you going to have? We will have normal stress. Okay. So, bending moment is going to generate normal stress coming out of the cross section, and that is sigma z z, correct. Whereas, due to torque, we are going to have shear stress tau theta z. Okay. So, we will have tau theta z in the theta direction, and then what will be the values of each of these. So, tau theta z for example, that is simply the torque T multiplied by the radius r divided by the polar moment of area, that j. And what is sigma z z? That is nothing but the bending moment m, which in this case is m x. So, m x, okay, and it comes with a minus sign into y divided by I x x, correct. And finally, what would be tau y z? Tau y z equals V y into q y divided by I x x into t thickness x, correct. So, if we look at the total stress matrix, we simply superpose all of them together, and then the sigma matrix in the cylindrical coordinate system, we have sigma equal to, see, the first step is always to get your sigma matrix at any point. So, we have sigma z z, which is minus m x y over I x x, then we have tau theta z, that is T r over j, T r over j, and then we have tau y z. Now, tau y z is acting in the y direction. So, we will have to resolve it along theta and the radial direction, is not it. So, think of any point here. So, we have this theta here, okay. So, this tau y z has got two components, one in the radial direction, which is this one, and in the theta direction, okay. So, the radial component, that is nothing but tau y z into sine of theta, correct. So, this is equal to tau r z, and then the theta component tau theta z, that is equal to tau y z into cos theta, okay. So, we can simply plug it here, and we have plus V y q y over I x x into T x into cos theta. Likewise, over here also we get plus V y q y over I x x into T x cos theta, and then tau r z, that is equal to V y q y over I x x T x sin theta, and then the same thing comes even here, and the rest all are 0. Okay, so, that is the state of stress matrix. Of course, you see in this coordinate system, none of the axes are principal axis. Suppose I want to use maximum shear stress theory again. Okay. Let us try to use max shear stress theory. To design the shaft. Okay. Now, looking at each of the components here, you have to notice that the shear force V y is actually constant, and that is equal to the applied load F. So, that does not vary along the length of the beam, whereas m x, that is equal to minus of L minus x into f. Okay. So, this number is 0 at the other end, and at the clamped end it is maximum. So, when x is equal to 0, m x becomes maximum at the clamped end. So, this is max at x equal to 0, and then the torque T is simply minus h f. So, that is also constant for different cross sections of the cylinder. So, what would be the critical point of failure? So, we see that the bending stress becomes maximum at the clamped end, whereas the other stress components, they are the same for every cross section. So, certainly the cross section at the clamped end is the critical cross section, right. So, we can make a remark here that the cross section at the clamped end is the critical cross section. Okay. So, let us now focus on that cross section. So, this is where x is equal to 0, all right, and actually this is z. You can recall that the cylinder axis is the z axis for r theta z coordinate system. So, this is actually z equal to 0, right, and then we have the x and y axis in the cross section. Okay. Now, where is the bending stress maximum in this cross section? So, looking at the formula for bending stress, sigma z z, that is equal to minus m x, and m x is equal to minus L f. So, this becomes L f into y over I x x. So, it is just a function of y. So, wherever y is maximum, that is where bending stress is maximum. So, these are the points where sigma z z is max. Okay. What about the shear stress? So, tau r z for this cross section is f into q y over I x x into T x into sin theta, right, and q y becomes maximum when y is equal to 0. So, everywhere on this line we have tau r z getting maximum due to q y, but then you also see it is multiplied with sin theta, right. So, when theta is equal to 90 degree, that is when tau r z becomes maximum, and so that is the point only at the center. So, this is the point where tau r z is max, but then you see at that point bending stress is 0, sigma z z is 0 here. What about tau theta z? So, look at the formula for tau theta z, and that is equal to T small r over j plus V y q y over I x x T x times cos theta. Okay, so, it has got two components. The first one tells us that it becomes maximum when small r is equal to big R. So, on the periphery of the cross section. The second component, that is V y q y over I x x T x. So, this is again getting maximum when q y is maximum, right. And where is Qy maximum? That is again on this red line in the cross section, right. And then what about cos theta, when does it become maximum? So, that is the point over here, right. Also see the value of t, t is minus hf. So, this is minus hf, whereas Vy is f. So, the first one comes with a negative value, where the second one comes with a positive value. So, if both of them have to be combined maximum, then it would be when the second component cos theta becomes minus 1, right. So, we have two points here on the red line, and out of these this is the point when cos theta is equal to minus 1, right. So, that is the point where tau theta z becomes maximum. Correct. So, you see the three stress components tau theta z, then tau r z and sigma z z, they attain maximum values at three different points. So, it is not such an easy problem now. So, what should actually be done then? So, it becomes a numerical problem, we cannot handle it using paper and pencil. So, look at this stress matrix. We know what is the value of torque T, we know what is the value of J. So, for every point in the cross section, we evaluate the stress matrix, find out the values of lambda 1, lambda 2, lambda 3 for different points in the cross section, and then get lambda 1 minus lambda 3 by 2. So, there will be a point in the cross section where the value of lambda 1 minus lambda 3 by 2 will attain the highest value, okay. And that is the critical point in this cross section, which is on the clamped end, and we can no more handle it using paper and pencil. We have to use, for example, computer to solve this problem, okay. So, you can notice a very simple design of a shaft or of a lever finally led us to a matrix which could not be handled using paper and pencil, and we had to resort to computer programming. You can think of when the machine is very complex, it has got so many parts, it would indeed be impossible to design it using paper and pencil, and you have to resort to computer programming. Okay, so, we can stop this problem over here for design. So, this completes our topic of theory of failure. One of the limitations of the things that we studied in this course is that we looked at stress strain behavior which was purely elastic. So, stress being proportional to strain, but there are materials which are not elastic. There are concepts of plastic material, viscous material, viscoelastic material or thermoelastic material, which have got their own stress strain relationship. So, let us cover some of them in brief details here, and with that we will end the course. Okay. So, the concept of thermoelastic material, for example, so in case of thermoelasticity, basically we have to think of how to model the stress strain relationship when we heat the body. So, suppose you have a body and you are heating it, what happens? It simply expands, right, but then no stress develops in the body. So, the extra strain, that is called thermal strain, and that does not induce any stress in the body. Okay. And it turns out that the thermal strain is proportional to temperature, and the proportionality constant is actually the thermal expansion coefficient. Okay. So, thermal strain, if we denote it by epsilon T, so that is your thermal strain this is proportional to temperature, and this turns out to be alpha times the temperature, where alpha is the proportionality constant, and this is also called thermal expansion coefficient. And this part of the strain is not responsible for generating stress in the body. So, suppose you have got total stress epsilon, then you have to subtract this epsilon T, and the remaining strain is the one which generates stress in the body. So, we have to simply modify our 3D Hooke's law in the following way. So, epsilon xx is the total elastic strain, we subtract epsilon T, which is minus alpha T, and then this becomes 1 over E into sigma xx minus nu times sigma yy plus sigma zz, okay, which also means that epsilon xx equals 1 over E into sigma xx minus nu into sigma yy plus sigma zz plus alpha times the temperature T. Likewise, for epsilon yy we have the usual term plus alpha times the temperature T, and this T is actually the change in temperature. Okay. So, suppose you have a material at room temperature and you heat it by 30 degrees, then this T would be 30, a change in temperature. Similarly, we have epsilon zz, the usual term plus alpha times T. So, temperature only affects the normal strains, it does not affect the shear strain. So, temperature only changes the length of line elements, it does not change the angle between two line elements. So, that means the shear strain, shear stress formula, they are unaffected. So, which implies your gamma x y is simply tau x y divided by g, then gamma y z is tau y z divided by g, the shear modulus, and gamma x z is tau x z divided by g. Okay. So, this is the 3-dimensional thermoelastic stress strain relation. So, we can write it here, 3-dimensional thermoelastic stress strain relation. Okay. Similarly, we have also got the concept of plasticity, for example. So, suppose you have got a steel bar and you are doing uniaxial test. Okay. So, the stress applied is sigma and the strain, the longitudinal strain is epsilon, and if we plot stress versus strain diagram, then initially it is a straight line which is the regime of linear stress strain relationship that we covered in this course, and then it becomes curved. Okay. So, this part where it gets curved, that is the regime of non-linear stress strain relation, because the slope is changing now. but the body is still elastic, which means from any point over here, if you come back, it is simply going to trace the original curve. But then after this point, this is a point where the body yields. So, this is called the yield point, and beyond the yield point, if you further increase strain, there is no change in stress, it remains almost flat. Okay. And then at a point it then breaks. So, this is where it breaks, this is called the yield point. So, this is a regime where the body has yielded. So, body has yielded here, and that is also called the regime of plasticity. It is the plastic regime. So, if you, for example, let us say you are loading it, you come to this point and then you start decreasing your stress, then you will no more follow the original curve, you will simply come down like this. So, that is the unloading curve. Okay. And when the stress becomes 0, you still have some strain remaining, and that strain is called plastic strain, epsilon p. All right. So, you see the original curve is actually quite complex, is not it? You have the linear elastic regime, then you go into non-linear elastic regime, then your body yields, and then if you increase your strain, there is no increase in stress, or with even slight increase in stress, there is a lot of strain generating in the body, and that is because the body has yielded, and therefore, the curve is almost flat. And if you keep on further increasing your strain, then at one point it will simply break. Okay. So, this is the curve for ductile materials. So, we have this curve for ductile materials. Steel is an example of ductile material, okay. But then we have also got something called brittle material, for example, glass. So, for brittle material, when you draw the stress strain relationship, it will simply be linear, and then at one point it simply cracks, there is no yielding for brittle material. Okay. So, for brittle material there is no yielding. So, you can see whenever you apply lot of strain, you get into such complex regimes, and we have of course avoided such regimes. We were just happy with linear stress strain relationship, and lot of things happen when the deformation becomes very large. So, this is of course covered in advanced theory of elasticity or advanced solid mechanics. Okay. So, with this I am going to end this lecture and also this course. So, I hope you enjoyed this course. If you have any queries on any of the video lectures, please feel free to write to me at my email address, which is ajit.k@am.iitd.ac.in. Okay. All right. Thank you.